Hey guys, welcome back to our channel. In today's story, we are going to talk about Niels Bohr's atomic model. More specifically, about the experimental evidence led to the validation of Bohr model. So what was that experiment proved Bohr's story? Let's talk about hydrogen spectrums. But before having discussions about hydrogen spectrums, there are some terms and knowledge that we should be aware of. First, electromagnetic radiation. Electromagnetic radiation consists of electromagnetic waves. These waves are separate electric and magnetic fields that are oscillating perpendicular to each other. Also, they are perpendicular to the direction of wave propagation. The light we see every day is a type of electromagnetic radiation. Ultraviolet light, infrared light, and other examples of electromagnetic radiation. If we consider all the electromagnetic radiation together, they inherit a very specific characteristic. That is, in a vacuum, electromagnetic radiation moves through at a specific speed. We call that as the speed of light. And this speed of light is 3 into 10 to the power 8 meters per second. And they have wave-like characteristics. Let's see what these wave-like characteristics are. Waves consist of peaks and troughs. The topmost points are peaks and the bottommost points are troughs. The distance between two adjacent peaks is called a wavelength. Wavelengths are measured in any unit that is used to measure distance, like nanometers, meters, even kilometers. Amount of wavelengths that pass a given point in a second is called the frequency. Frequencies are measured in hertz or per second. Waves are periodic. This is the wave equation. Anything that behaves according to the wave equation are called as waves. Simple c is the speed of the wave. Nu is the frequency of the wave. Lambda is the wavelength. From this equation, you can see that the speed of the wave is a constant and therefore the frequency is inversely proportional to the wavelength. Let's see how the knowledge in waves can be applied in the wave equation using simple maths. Yellow light has the wavelength of 589 nanometers. How can you calculate the frequency of this radiation? Okay, first we need to identify what equation are we going to use in this question. We have given with the wavelength and have asked to find the frequency of the radiation. So the equation we have to use in this question is the wave equation. C equals nu lambda. They have given the lambda to be 589 nanometers. We know from our previous knowledge that the speed of radiation in vacuum is 3 into 10 to the power 8 meters per second. Now let's plug these values in our wave equation. So we can divide the speed of light over the wavelength to find the frequency of light. Values simplify to 5.09 into 10 to the power 14 Hertz of frequency. You can keep the units of this final answer in both per seconds and in hertz. Either way is fine. Yellow light is a single type of electromagnetic radiation. Different types of electromagnetic radiation have arranged in different positions according to their wavelength or frequency. The display of electromagnetic radiation arranged in order of their increasing wavelength or decreasing frequency is called electromagnetic spectrum. In this spectrum, from left to right, the distance between two adjacent peaks increases. So the wavelength increases. If the wavelength increases, frequency should be decreasing. So the energy. We'll see how energy decreases with the frequency in a little bit. So the highest energy radiation is gamma rays, then X-rays, ultraviolet, and then only comes the visible light. Then infrared, radio waves, radar, TV, FM, all comes next. From this electromagnetic spectrum, only wavelength visible to human eye is from 400 nanometers to 700 nanometers approximately. We call that region as the visible region. In 1900, German physicist Max Planck said energy can be quantized. Energy can be what? Quantized. Not a big deal, just a big word. Let's see it like this. Can you see this staircase? The boy on the top of the staircase can only stay in a step. He can only move from one step to the other. Intermediate step is not possible. Nobody can stay in between two steps. Boy can't come to the half step. Like he can only climb up or down a stepwise. Energy can be released or absorbed in fixed amounts. Quanta. That is quantization. So Max Planck, considering this quantization of energy, proposed that energy of a quantum is directly proportional to the frequency of radiation. Proportionality constant comes in Planck's constant. This is how the energy becomes directly proportional to the frequency. In 1905, Albert Einstein, extending Planck's quantum theory, deduced that radiation behaves like energy packets. Each packet of energy is called a photon. E equals h nu expression was for the energy of a photon. Let's move into another calculation to see how this works. What could be the energy of 1 mole of photons with wavelength of 305 nanometers? They have given us the Planck's constant and the speed of light as additional data. To find the energy of radiation, we need frequency. To find the frequency, wavelength is given. So we can use the wave equation to find the frequency. Speed of light we know, and we know the wavelength. Found frequency value could be plugged into the Einstein equation as the Planck's constant is given. So we get the energy of a photon as 392 kilojoules. I'm going to ask you a question now. What would you feel if I tell you that high heels were originally men's shoes? Scientists identified radiation, which were waves initially, seems to have particle properties too. Louis de Broglie extended his idea that radiation under certain conditions can act as waves and under some other conditions behave as particles. This was called the wave-particle duality of radiation. Talking about high heels, they were men's shoes. They were worn by Persian soldiers to help their boots when riding horses. De Broglie's suggestion was not limited to radiation. He talked about electrons too. He said the electron moving around the nucleus of the atom, being a particle, can behave as a wave too. Therefore, it should have a wavelength. He calculated this wavelength as a division product of Planck's constant and momentum. He proposed this wavelength of electron, like any other particle, is dependent on the mass of the particle and the velocity. De Broglie's hypothesis was for all matter. He said any object with a mass and velocity could give rise to a wave. Now you might wonder if a volleyball or a train, even us people, are associated with a wave. Yes. Seriously? Yes, of course. However, compared to the size of the object, waves could be unobservable. But for the case of electron, since it's too small, wave properties are quite noticeable. Since all the talk regarding the electron, let's go back to the atom. In a previous video, we talked about the Bohr model of atomic structure. Bohr model was based on experimental observations. Bohr could explain experimentally obtained hydrogen spectrums through his model. Bohr model was developed to explain hydrogen spectrums. This is about hydrogen spectrums. It could be a continuous spectrum, like this. It doesn't have any apparent gaps or breaks through its wavelength range. It could be a line spectrum, like this. Here we have two types of line spectra. One is emission spectrum and the other is an absorption spectrum. Atoms have electrons in their energy levels. When we supply energy to an atom, electrons absorb energy and make transitions. When electrons absorb energy from the visible region, we see black color lines in the illuminated background. These black lines are due to the absorbed photons of energy. This is given in the absorption spectrum. When electrons absorb energy, they move to high energy states. These high energy states are not stable. Therefore, they move back to their initial energy state. During the transitions, absorbed photons of energy are released. These photons mark a line in their respective wavelength. That is how we see colored lines in a black background. This is the emission spectrum. Let's see how Bohr talked about atomic spectra. Specifically, how he built up his model based on hydrogen emission spectrum. In an atom, each orbit corresponds to a different value of n. We call this as the energy level. The distance between two energy levels decreases as the n value increases. Let's label these energy levels as 1, 2, 3, 4, 5 and 6. In hydrogen atom, if the single electron is in the first energy level, we call this as the ground state. When energy is supplied, the ground state electron absorbs the energy and excites into a higher energy state. This is called the excited state. This state could be the second energy level, third energy level, fourth energy level, or anything. Once excited, let's say to the sixth energy level, this high energy state is not stable, just like life. Now, the electron wants to come back to the ground state. This is called relaxation. Relaxation can happen in many ways. From 6 to 5 to 4 to 3 to 2 to 1. Or from 6 to 4 to 3 to 2 to 1. Or from 6 to 4 to 2 to 1. So now you should be able to figure out that there could be many possibilities of this electron to relax into the ground state. Let's organize these possibilities according to the final state of each of the transition. Electron can relax to the first energy level from the sixth energy level, fifth energy level, fourth energy level, third energy level, and from the second energy level. How did the electron end up at the second energy level? Again, from the transitions from sixth energy level, fifth energy level, fourth energy level, and third energy levels. Electron relaxes into the third energy level from sixth energy level, fifth energy level, and fourth energy level. This repeats as to the fourth energy level and fifth energy level as relaxation. These are the transitions from higher energy level to lower energy level. Depending on these transitions, we can sketch the spectrum. When the transitions occur, respective photon of energy is released, and that energy mark a line in a blank photographic plate. Let's start with the highest energy transition, from sixth energy level to the first energy level. Then the second highest energy transition, from fifth energy level to the first energy level. Then the third highest energy transition, from fourth energy level to the first energy level. If we compare the energy gaps between these transitions, the energy difference between the transitions from sixth energy level to the first energy level and fifth energy level to the first energy level, it is much smaller than the energy differences between the transitions from fifth energy level to the first energy level and from fourth energy level to the first energy level. Therefore, the gap between first two transitions should be smaller compared to the gap between second two transitions. Transitions from third energy level to the first energy level should be further away, and the line comes from the transitions from second energy level to the first energy level should be far away because of the energy differences in these levels. Now, the next set of transitions. Here, everything ends up in the second energy level. Compared to the first set of transitions, these are much less in energy. Keeping that in our mind, let's sketch the first transition quite away from the first set. Then the second transition, from fifth energy level to the second energy level. We can see that comparing energy gaps, the energy gap between the first two transitions of the first set and the first two transitions of the second set are similar. So, the gap in the spectrum should be the same. This repeats in the rest of the transitions too. So the difference between the first set of spectral lines from the second set of spectral lines is the missing last energy transition. Similarly, in the third set, it should be the second set of spectral lines but without the last minimum energy transition. Okay, how can you place this set? Like I said, it should be the same second set of spectral lines except the smallest energy transition. So the gap between the first set of spectral lines and the second set of spectral lines is due to the energy difference between the second and the first energy level. The gap between the second set of spectral lines and the third set of spectral lines is due to the energy difference between the third and the second energy levels. As the energy difference between the third and the second energy level is much smaller compared to the energy difference between second and first energy level, the gap between the second and third spectral lines should be smaller than the gap between the first and the second spectral lines. Now, can you predict the positioning of the fourth set of spectral lines? There are two transitions, so there should be only two spectral lines with an energy difference similar to the energy difference in the first two transitions of each set. Energy gap between the fourth set and the third set of spectral lines is due to the energy difference between the third and the fourth energy levels. So the gap should be smaller than the previous. If we extract the spectrum alone, you will see nothing else except a set of lines. But it is already an ordered set of lines. What is the order here? Remember, we started with the highest energy transition. So the direction gives the increasing energy or frequency. And we can label these sets of spectral lines. All the transitions that relaxes into the first energy level is called the Lyman series of the atomic spectrum. Transitions to the second energy level is Bohr series. Transitions to the third energy level is Paschen series. Transitions to the fourth energy level is Brackett series. If we consider a single series to the direction of increasing frequency of energy, lines of a spectrum gets closer. If we consider series to the direction of increase in energy or frequency, distance between series increases. These series do not appear in the same region. As you can see, with the frequency, the positioning of series vary. For example, Lyman series locates in the UV ultraviolet region of this electromagnetic spectrum. Bohr series locates in lesser frequency, that is the visible region. Partition series locates in the IR region and partition series overlaps with the bracket series. So from all the series in the atomic spectrum, only thing we can see is the Bohr series. In the hydrogen atomic spectrum, it appears as this to the human eye. Here we see some colored lines. What is the direction of frequency here? Spectral lines get closer from left to right. So from left to right, frequency should be increasing. The red color line here represents the lowest energy transition of the Bohr series. We call it as H alpha line. Usually it is the transition from third energy level to the second energy level. Green color line, H beta line, is the second lowest energy transition, and that generally is from fourth energy level to the second energy level. H gamma line appears in blue in color, and that gives the transition from fifth energy level to the second energy level. H delta appears in violet in color, and that is due to the transition from sixth energy level to the second energy level. So likewise, Bohr could explain how energy levels are positioned in an atom, how the hydrogen single electron stays in an energy level, and how the whole Bohr model was based on hydrogen spectrum. However, Bohr model could not explain how the spectral pattern works with multi-electronic systems. So, Bohr model was only applicable for single electronic systems. Also, he could not explain how spectral patterns affect in the presence of an electrical or magnetic field. Let's see how today's story worked for you. First statement, the emission spectrum of the hydrogen atom and the emission spectrum of lithium 2+ ion are very closely similar. Hydrogen atom contains only a single electron, okay. Lithium 2+ ion contains only a single electron, that is also fine. If you consider the number of spectral lines you get in each case, yes, it is the same number of spectral lines. But the spectrum as a whole, is it closely similar? I'm going to go with no. Even though the number of spectral lines are similar, because of the positive charge on lithium, relative positioning of spectral lines might differ. Hence, you will not see a closely similar spectrum for the two. Second statement. Hydrogen atom and the lithium 2+ ion have only one electron in each of their outermost energy levels. That is true without any doubt. What could be the correct statement? The radiation corresponding to the n equals 2 to n equals 1 transition has the highest wavelength. Incorrect. There are more energy involving transitions. Even n equals 3 to n equals 1 is a more energetic transition. The n equals 3 to n equals 2 transition corresponds to the H alpha line. That is true. We learned that a short while ago. Can you remember the color of the H alpha line? It was red. The first series of lines occurs in the IR region. No, it occurred in the ultraviolet region, and the series in the IR region was partition. In a given series, the separation between adjacent lines increases in the direction of increasing energy. No, separation decreases in a given series. Emission of radiation occurs when electrons undergo transitions to highest levels from lower levels. That is absorption. Emission of radiation occurs during relaxation. That is the transition from high energy states to low energy states. To wrap up today's story, we talked about electromagnetic radiation, wave-particle duality, hydrogen spectrums, and Bohr theory and its applicability to hydrogen spectrums. If you got anything, write us on ilearn.sled@gmail.com. Subscribe to our channel for more cool videos. We'll see you with another fun lesson. Have a nice day, guys. See you.